Hey guys, Algebra 2, welcome back. Let's talk about your next assignment. I'm going to prep you for the next assignment, and at the end of this video, I'll give you some more details on that. First, let's review going from radical to exponential form. For exponents that have fractions in them. So rational exponents, so 1 over n or m over n. These are the two rules that we outlined in the previous video, and these are the two rules that are truly going to carry us through this entire second assignment. Let's see. Example number 1. Let's just try some of these out. For example number 1, if we look directly at this reference right here, we can see that it's actually more closer to, I guess I'll call this number 1 and number 2. It's actually closer to number 1. Here we have the square root of x to the fourth. And what you can't see here is the index. The index here, whenever it's not written, the index is 2. Okay, so at least for this case, this would be a 2 here, but we usually don't write that in general. Let's see, moving on. Let's see, we can write this in exponential form by using the property number 1 above. If we look there, let's see, property number 2 actually, mistake. Property number 2. Property number 2 says that I can rewrite this as x to the power of m over n, and here the numerator is going to be 4 divided by the denominator, which has to be the index 2, okay? And 4 divided by 2 is just 2. So we can see that this simplifies out to just x squared, and that would be written in exponential form, as simplified as it gets. Let's move on to number 2, where we will use property number 2 once again. Let's see, let's write this out. 3, the cube root of x to the 12th. Okay, using the same exact property, this means that this equals x to the power of 12 divided by 3. Remember, 3 is the index, 3 always goes in the denominator. Okay, 12 divided by 3 is just 4. So it simplifies out really easily like that. Okay, let's keep going. Another example. Index is 4 this time. The fourth root of x squared, index is 4. This is going to be equal to x to the power of 2 divided by 4. Our index has to go in the denominator. Okay. We can simplify this a little bit, but it's still going to be a fraction at the end, but that's okay because exponential form just means that we need something in the power. 2 divided by 4 can be simplified to 1/2. So we're done with that. Okay. Let's see. And actually, with property number 1, we could also write this as the square root of x because our index is technically 2 if we were to rewrite it that way. But since it asks for exponential form, that's where we'll leave it for this example. Okay, let's go into some numbers now. Okay, simplify the radical below. Now, sometimes when you simplify radicals, it can be really easy. Like, for example, if you take the square root of 64, you get a nice clean number 8. But if I were to take the square root of 50, you'll notice that I don't get a nice clean number, so I can't simplify it by just typing it in and seeing what happens. Now, to do this, I have to notice what the index is. And now we have to factor out any perfect, and since the index is 2, we're going to factor out any perfect squares. If the index was 3, we would factor out any perfect cubes, and we might get to that later on in this video. To factor out perfect squares, it's good to just write down what you know perfect squares are. 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, and so on. And you're looking for one of these numbers to divide evenly into 50, and we can see a good contender right here already is 25, or 5 squared. Okay, so we're going to use this in our problem. This is equal to the square root of, and I'm just going to factor out what 50 actually is, 25 times 2. And the reason we used a perfect square is because there's another property that we can use here. It's the fact that whenever I have two things being multiplied underneath a radical, I can actually split the radical up into two different radicals being multiplied. So this equals the square root of 25 times the square root of 2. Luckily, we know what the square root of 25 is. In fact, that's why we use numbers from the list. The square root of 25 is 5 times the square root of 2. So this would actually be the most simplified form of the square root of 50. Okay, let's use that exact same technique for number 5. We're also going to need to factor out any perfect squares, so I'll leave that on screen. So we're looking for two numbers that I can multiply together to get 12, and one of them has to be from this list of perfect squares. Notice that the number 12 is pretty small. In fact, we only have two options, 4 or 9, and only one of them is going to work. I know for a fact that you can divide 12 by 4 and get 3. 4 times 3 equals 12, so I can split it up like this. And then I can split up the radical, which is the whole point of finding and factoring out that perfect square. The square root of 4 is 2. Therefore, the square root of 12 can be simplified to 2 times the square root of 3. Okay, for this example, this will help. All of the examples in the rest of this video are going to help you out on problems 6 through 10, which are really the more challenging problems on the DeltaMath assignment. We need to rewrite the following expression as a simplified radical and then write it in exponential form. And you'll see down here I have boxes for both of those, and I'll zoom out at the end so you can see all the work shown. Let's see. We need to write it as a simplified radical first. So simplified radical is exactly what we were doing on the previous examples. Here, this would be a simplified radical, but this time we have x's and y's, and we'll deal with that, and I'll show you how to deal with that here in a second. First thing I want to notice is that the index of my radical is 2. So I know that we're taking square roots. It's not written here, but that is just common. It's tradition for math. If you don't write anything in that index, it has to be 2. It's the square root. I'm going to start by writing just the 17 out front because we're not going to touch that quite yet. And what I'm going to do first is split up my radical into different parts. Since I know that I can rewrite any multiplication underneath the radical as multiple radicals, I can just do that. This is the square root of 20 times the square root of x squared times the square root of y to the power of 5. Okay, there's a couple things we can do here. First of all, just like on the last example, I can rewrite the square root of 20 as a product of any perfect squares. Remember, perfect squares, let's get a list going. 16, 25, 36, ... Okay, we need to rewrite 20 as a product of a perfect square and another number, and I already see right off the bat we can use the number 4 here. We can write this as 4 times 5. And we'll deal with that later. Let's deal with the square root of x squared first. Okay, now since x can be any number, I just want to point this out. This is the technicality. Since x can be any number, whenever you take a negative number and square it, you get a positive number. Let's say that x equals -1. -1 squared is 1. Okay, if we take the square root of 1, we get 1. We don't get x. So this is actually the absolute value of x times the square root of y to the 5th. And I'm going to rewrite that here in a second. Since I want to factor out any perfect squares, I have to notice that y squared is equal to y to the 4th. So y to the 4th is actually a perfect square. So we can split that off from the bunch. Oh, excuse me. If we factor out a y to the 4th, we're going to be left with y to the power of 1, thanks to that addition property for exponents. Now that we're here, I'm just going to ignore the fact that x is absolute value here for a second, because we're going to get to that next week. So I'm going to ignore that, and you won't need it for the DeltaMath assignment either. Let's see. Let's simplify some things. This is equal to 17 times the square root of 4 times the square root of 5. Okay, given that this can be broken up into these two parts, times just x, no square root here, times the square root of y to the power of 4 times the square root of y. Okay, let's continue simplifying here. This is equal to 17 times the square root of 4 is actually just 2 times the square root of 5 times x. Okay, the square root of y to the 4th is y squared. Okay, you can think of that as y to the power of 4 divided by 2 using property number 2 from the very beginning of this video. 4 divided by 2 is just 2. So we can think of that as y squared times times the square root of y, and you'll notice that we have two parts that can't be simplified. So we're going to combine those here at the end. Okay, let's see. 17 times 2. I'm not that good at 17 on my multiplication table. 17 times 2 equals 34. So this equals, and let's move some of the not square root parts over to the left because it doesn't matter. These are all being multiplied. So we got 34 x y squared, okay, times the square root of 5 times the square root of y. And since I can split apart radicals when they're being multiplied, that means I can do that backward as well. So when we finally write this in a simplified radical form, we're going to just combine those two terms. This is equal to 34 xy squared times the square root of 5y. And that's really all there is to it to write it in simplified radical form. You're just pulling out all those perfect squares that you see. And really, since I know that the index is 2, it's really just pulling out all of the even powers. Like we pulled out an even power of y. We pulled out an even power of 2. That's 2 squared. And we had to do that in order to write it as a simplified radical. To write it as an exponential form, what we have to do is realize that the square root of 5 is just 5 to the power of 1/2. Since my index is 2, and that the square root of y is just y to the power of 1/2 in the exact same way, because my index is also 2. And since exponential form is just the same thing, but with powers instead of radicals, we can just rewrite this statement as 34 xy squared times 5 to the power of 1/2 times y to the power of 1/2. And that would be exponential form for this. And as you can see, the difference between the two forms is that there are no radicals underneath exponential form, which was our goal. Okay, let's do a few more of these. Okay, this example is very similar. In fact, what's convenient is that we still have an index of 2. So we're still looking for perfect squares. And the instructions are the exact same as the previous example number 6. Okay. Let's try this out. First thing I'm going to do is leave everything on the outside. It doesn't need to go in the radical. In fact, when you simplify the simplest radical form, you're trying to get is the least amount of things underneath the radical as possible. So let's try that out. The square root of 16, I'm just going to separate everything out. X to the third, square root of y to the third. Okay, since those three are being multiplied underneath the radical, that means that I can split them up. Luckily, I know that from my list of perfect squares, 4, 9, 16, 25, I actually know that 16 is a perfect square on its own. So let's take care of that first. 2 times x times square root of 16 is just 4. Okay, now I'm going to split up these two terms, and I'm going to notice that they both have the power of 3 on top. And to factor out any perfect squares, we need to just take the x cubed term and turn it into x squared times x, okay, because the exponents will add up to 3, and the same for the y cubed. Okay, because these are the perfect squares that we want to factor out. So this is going to equal square root of x squared times the square root of x times the square root of y squared times the square root of y. Okay. Let's see, we can simplify these two terms. Square root of something squared is just that thing. So this will equal 2 times 4 is 8x times x times the square root of x, which we can't simplify, times y times the square root of y, which we also can't simplify. Now I'm going to multiply everything that's not underneath a radical together on this next step. And then I'm going to combine these two radicals as well for the last step. This equals 8 times x is 8x squared. We also have to multiply that by that y times the square root of xy. Okay, so you can see here, I've color coded it pretty nicely. You can see that all the parts outside the radicals that we pulled out ended up on the left, and everything else got combined into one radical at the end. So this actually is the simplified radical form. Okay, And if we continue writing this in exponential form, all we have to do is take the previous step and realize that, okay, square root of x is x to the 1/2. Square root of y is y to the 1/2. Okay, let's see. This will be equal to 8x squared y times x to the 1/2 times y to the 1/2. Okay, and let's actually take this a step further. If I multiply two things together and they have the same base, like these two terms here, I can add their exponents to simplify them further. Okay. For example, 2 plus 1/2 is 2.5, which is just 5 over 2. And let's see, 1 plus 1/2 is 1.5, which is 3 over 2. So we can actually rewrite this as 8 times x to the 5 over 2 times y to the power of 3 over 2 by adding up those exponents. So these exponents got added together to 5 over 2. And this is exponent of 1 got added together with 1/2 to get 3 over 2. So these would be the two solutions. Now for the first couple of problems on DeltaMath, you're only going to be worried about simplified radical, but I believe the last two you're going to have to know how to do this. Luckily the last two are multiple choice, so it should be a little bit easier. Okay, let's do another example. This one is important because my index is now 3. So I'm not going to be worried about perfect squares. I'm going to be worried about perfect cubes. If you take 2 cubed, you get 8. If you take 3 cubed, you get 27, and so on. We're looking for those perfect cubes. And you'll also notice some other things that'll make this a little bit easier. Just like for square roots, we can break apart anything being multiplied from a radical. And just like the last examples, we're going to leave everything that's outside on the outside at first. The cube root of 8, and don't forget to write the index each time that you write the radical, so you don't forget it's not a square root, times the cube root of x to the power of 6 times the cube root of y to the power of 9. Okay, now I'm noticing these two terms and I'm realizing, oh, I could use rule number 2 here that says that if you have the nth root of a to the m, that just equals a to the power of m divided by n. So we can use rule number 2 to simplify these two terms. Okay, also notice on my perfect cube roots list, I already know that the cube root of 8 is 2. So this equals 3 times y times 2, okay, times x to the power of something. So we have to use rule number 2 here. The index is 3 and the power is 6, so the fraction is going to be 6 divided by 3. Okay, and we'll use the exact same rule for this next term. This will be y to the power of 9 divided by 3. This is going to be equal to 3 times 2 is 6y. Okay, x is to the power of 6 divided by 3. 6 divided by 3 is just 2. And y is to the power of 9 divided by 3, which is just 3. Now, it looks complete, but we can actually combine the two y terms at the very end to write this as 6x squared times y to the power of 3 plus 1, which is, not written, but we know it's there. 3 plus 1 is 4. So this is one of the bizarre cases where, in fact, the simplified radical form is the same as the exponential form, because we can completely eliminate the radical. The radical is actually not actually necessary to complete this problem. Okay, last example. Stick with me, guys. Fourth roots. So we're looking for perfect fourths, and that should make you suspicious right away. 2 to the power of 3 is 8. If we take 2 to the power of 4, we just have to take that number times 2, and we'll get 16. So we know that the fourth root of 16 is actually 2, and we can take care of that later. The other thing you want to notice is that we need to be factoring out multiples of 4 in the powers. Okay, so for example, x to the power of 10 can be written as x to the 4th times x to the 4th times x squared. And since we only want perfect fourths, I'm going to combine those two x to the 4th to get x to the 8 times x squared, because 8 is divisible by 4, and we'll use that fact later. Y to the power of 12 can be rewritten as y to the 4th times y to the 4th times y to the fourth, because if you add up 4 plus 4 plus 4, you'll get 12. And it turns out that this is evenly divisible by 4 already, so we can just use y to the power of 12 here in my example. Okay, so let's try this out. This equals the fourth root of 16 times the fourth root of x to the 10, and I'll deal with that later, times the fourth root of y to the 12th. Okay, fourth root of 16 is just 2. Okay, and let's see. Let's actually use a different technique to write this last part. Well, actually, never mind. I'm just going to do what I was doing. This will be the fourth root of x to the 8th times the fourth root of x squared. Okay, that's because I'm using this fact over here. I'm using this fact over here that I can rewrite it like this, and then I'm splitting up the radical. Okay, next thing I'm going to do is multiply that by the fourth root of y to the power of 12. And now let's start using some of our rules that we know. Okay, this equals 2 to the power of, if I rewrite this in exponential form, this term becomes x to the power of 8 divided by 4. If I rewrite this in exponential form, I get x to the power of 2 over 4. And if I rewrite this using rule number 2, I will get y to the power of 12 divided by 4. Okay, some of these are going to work out easily. Some of them we're going to have to deal with later when converting between the two forms. 8 divided by 4 is just 2, so that becomes x squared. 2 divided by 4 is 1/2, and that's what we're going to have to deal with between the two forms, but that should be pretty easy. And 12 divided by 4 is just 3, so that'll stay simple. Okay, now in exponential form, let's deal with that first, because for exponential form, we need all the terms simplified in exponential form. If I take x to the power of 2 times x to the 1/2, I need to add up the exponents. 2 plus 1/2 is 2.5, which is just 5 over 2. Okay, so that's what we can use for exponential form. Okay, for simplified radical form, we're going to have to realize that x to the 1/2 is just the square root of x, using rule number 1 from the very beginning of this video. Okay, let's do exponential form first. If we combine these two terms, we get 2 times x to the 5 over 2 times y cubed, and that'll be the answer for exponential form. Okay, for radical form, we're going to have to rewrite this as 2 times x squared times y cubed, and you usually just put the radical at the end. It's just a tradition to put the radical at the end. We'll put that square root of x at the end, and that's as simplified as it gets if we're leaving the radicals in place. Okay, let's talk about your assignment and what you should be doing this weekend and next week. Okay, real quick, let's talk about assignment number 1. If I go over to the student data for assignment number 1, as you can see, a lot of people have not started their online assignments, and that's just inconvenient for me because I have to call home next week if you do not participate in class, and number 2, because I can't make sure that we're ready to move on to the next part. I'm moving on anyways. We are going to move on to assignment number 2. You can find assignment number 2 on DeltaMath as well. I'm going to post it soon. This will also be open until April 3rd, but in order to not get behind, you guys should really start on these 2 assignments. This video should take you through it pretty easily. It's pretty lenient with the attempt numbers, just like assignment number 1, and there are no random problems. So if you retry a problem, it's the same problem as the one before, and I'm just doing that to make things a little bit easier for you guys. Other than that, like I said, you would want to pause at the beginning of this video when you're looking at those 2 rules. Pause on any part that you need. If this video was too long, I don't care if you watch it at 2 times speed. That's fine with me too. Otherwise, you can go to DeltaMath for your next assignment and hopefully complete that, at least assignment 1 by this weekend, so that way I can know where we're at and how fast I should be going with this online course. Like I said, email me or message me on Canvas if any technical difficulties arise, or if you can't access DeltaMath for any reason, let me know. Because like I said, next week I will have to start calling home if I don't get participation. So help me out, guys. Help yourselves out. Do some math. Have a good weekend and a good day as well.